want to know what quantum theory is. Now, so far, we've dealt with largely the math aspect of chemistry. Now we're going to switch to the counting part in terms of the electrons. So far, we've learned to count the electrons, and we know how many electrons there are, but we don't know where the electrons are located, other than to say the electrons are in the electron cloud, right? Now we need to be more definitive about the electrons. And so quantum theory is going to talk about the electrons and where they are in the electron cloud. You remember when you drew a model like this? Some of you probably built models that look like that. I still teach it in physical science. Technically, it's wrong. Okay? We're going to talk about what's wrong with the model in this particular unit. Okay? It's called Bohr's model. It has a name. Now, we're going to do more with that model than you ever wanted to know. But to start with quantum theory, we're going to talk about the wave-particle nature of light. A lot of these notes are typed because this is one of the things they changed in the new curriculum. They added in parts that I would have particularly added back into the curriculum. They had it out for about 20 years, and then they decided, no, let's stick that back in. So since I hadn't taught it in 20 years, I'm apt to skip over it. So I typed it just to make sure my old brain didn't just keep skipping over it. So I put it in. I can probably do it now without the typing, but since they're nice and typed, for those of you who don't like my handwriting, it's there. But I didn't type all of it, so you don't have to deal with it on some slides like this. So, the wave-particle nature of light. Once upon a time, scientists believed that electrons behave as particles. Okay? By particles, think of them as little tiny BBs. They have properties of matter, and they behave as such. So when they hit something, they would move it. Light, all right, they believe that light had properties of wave. Now, this is where I need you to have some background from middle school. Unfortunately, most of you don't have a lot of background from middle school, so I'm going to have to spend a little bit of time here today in the properties of wave. How many of you? Yeah. Yep. Yes. Okay. Yeah, we're going to talk about that when we talk about the photoelectric effect. And when we talk about neon lights and that, we'll get to that. All right. So when we talk about light behaving as waves, you remember things like frequency, wavelength, amplitude. You don't remember what any of them is? Amplitude is how I know. Yeah, that's good. I remember that from math class. Well, I'll take it any way I can get it at this point. Now, all right. Now, the important part of this is scientists discovered that electrons can behave as both particles and wave. Now, if an electron can behave as a particle and a wave, what does that mean about light? Yeah. Okay. So, it made sense to scientists that light can also behave as a particle and a wave. Now, at the time that scientists were making this discovery, this was pretty revolutionary. To say that an electron, okay, can behave as a wave, or that light could behave as a particle, that's pretty revolutionary. Okay? To say that light could behave almost as a BB, that light could strike, let's say, a piece of metal and knock a particle loose, that's not something that was happening up to that point that scientists could explain. All right, so we're going to walk through 2 examples of how that works. Probably not today, and probably be Thursday. Okay? So, in summary, both electrons, light, can behave as particles and waves. Right? And again, at this time, which was late 1800s, I think it was actually early 1900s. This was pretty revolutionary. Because electrons were only thought to be particles, light was only thought to be waves. Now, because electrons can be viewed as waves, we're going to spend pretty much the rest of class talking a little bit about waves and light and things you probably should remember from the middle school. Those of you who had a good background, this is all going to be reviewed for the rest of today. Those of you who had a crappy experience, it'll be largely new or a good review for you. Okay? Some of you may remember it from math class, like amplitude. Although amplitude is the only one you don't need to remember. You got no frequency and wavelength. All right, has everyone caught up? All right, so first of all, what is electromagnetic radiation? You can abbreviate that EMR so you don't have to keep writing it out. If I ask you for this on a quiz, which I will do sometime later this week, the answer is not EMR, by the way. When I say what is electromagnetic radiation, don't write EMR. Okay? A lot of you will. It's a form of energy. Okay? A form of energy that travels through space. In the form of waves. Next. The next part, I'm pretty sure, is where I have the space for the example. I feel confident that y'all can give me some examples of EMR, of electromagnetic radiation. Be more specific. Ultraviolet. There you go. Ultraviolet is what I want. X-rays. I don't take shorthand. Does everybody have this so I can go to the next board? Because I do not take shorthand so I can not write all these down or remember them all. All right, does everybody have the definition? And hold your examples for a minute. What, SPF? I don't know. Solar protection. Google it. Right. Come like this. Look it up. All right. So y'all said ultraviolet and X-ray. Those were 2. Did y'all say something else I missed? Hold up. What? Microwave. Oh. Give her name. Starts with I. What? Gamma rays work? Isolation rays. Isotonic waves. No. Radio waves? I'm trying to figure out what it is. Don't start with an I. I know. Isotonic waves.
Ah. That's work though.
What? Uh-huh. There's your heat waves.
Oh, the what? Infrared. Oh my God.
What about light?
All right, I need a name. Gotta have something else besides just light.
Solar spectrum. Oh.
Solar light.
Y'all all have access to it. I just haven't found it yet.
Electric.
Alexa's on the trail.
This is a little bit crazy that I actually have, like, does that have to work?
You say what?
Does that always have to work?
Yes.
So like, I'm just trying to think of the both sides.
Visible light.
Oh, it was on the first row. Not looking for it.
All right, where you at, Alexa? Where are the answers at?
The only one I actually kind of do is blue light.
Ah!
Oh, we gotta get that out.
I told you we might get to today.
But I'm trying to do it
You
off
look
the
on the
dome.
very back page of your stapled reference table. The very bottom. There's a cheat sheet. That's the visible spectrum. We'll get to that. Alright? But if you look at not where it has the colors, we'll talk about that maybe a little bit. Alright? But you're going to see the things relevant using that Emma has largely been getting off of the chart hanging on the door here. Alright? The radio waves, microwave, infrared are all there, ultraviolet, X-ray, and gamma. Alright? Those are all types of electromagnetic radiation. They're all there. Now, all of those electromagnetic radiations have two properties. How do we tell them apart? How do we know it's a microwave? It's not a gamma ray. We're not going to get cancer. There you go. Frequency and wavelength. Frequency and wavelength. And I'm not going to write anything else there, I'm pretty sure. Let me look. So you don't need to leave a bunch of space. Frequency and wavelength are how we tell them apart. Close together it is.
Oh, that's like, yeah, what's it called?
Everybody got it? Alright, so what is the electromagnetic spectrum? Alright, this is what is on your reference table. Okay? Now, basically, it shows all types of EMR. That's all it means. The electromagnetic spectrum shows all types of EMR. Now, the biggest thing you need to notice is this arrow right here. It shows longer wavelength, shows shorter wavelength. If they ask you something about which one has the highest or the lowest wavelength or frequency, you can't know the answer to that unless you look at this chart. Is the question going to say, use your reference table? No. You're going to have to know to pick up the reference table to find that information. Now, is frequency given on here? No. I'm going to teach you the relationship between wavelength and frequency in a little bit. And you'll know how to do that shortly. But you're going to have to know to look up this chart. Now, you see this right here? This is the itty bitty space where visible light lives on this chart, where I just colored in that blue section. Now, that's it. That's the only range that our eyeballs can see. All this out here, we can't see microwaves. We can't see infrared or radio. We certainly can't see ultraviolet where the sun comes down. If it could, we could see those hazardous rays that could cause skin cancer, and we could jump out of the way. Especially us dumb white people who try to lay out there and get some suntan in the summertime. All right? Now, hey, not all of us are good looking at tan like you are, Nada. So we got to lay out there and try to get some cover. All right? So,
I just lay on my floor.
Yeah, they don't get it. That thing hurts.
Okay, we put on some 45 SPF. We don't know what it stands for, but we put on some 45 SPF. It hopes that the UV rays don't get through to give us sun cancer and we get a little color. All right. So we have these colors, right? Now, all these colors are blown up for this tiny little space right here. Now, this is called what? What y'all learned this was called back in elementary school? Roy G. Biv. All right, everybody remember that? How many of y'all have never heard that? Every year I get people who are like, what are you talking about? All right. Most of you have heard it called the rainbow, right?
Oh.
Now, for those of you who've never heard this, the order of the colors down here are referred to as Roy G. Biv, so that you know the order of them. So red, orange, yellow, green, blue, I stands for indigo, and violet. So you put them in the right order. It's just a mnemonic device. Okay? Huh? We're going to talk about why you can see the rainbow, but it's got to do with sunlight coming through water left in the air, and the water acts as the prism, and then the light separates it based on wavelength. It is as part of our unit today and Thursday. Okay? Just because we can. All right, so what's the wavelength? The same reason. We're going to talk about it. What's the wavelength? Do not tell me the length of a wave. You'll get 0 points for that.
I literally just said that.
Let's just say we have a quiz later this week. Let's just say the definition of a wavelength is a question, and you write the length of a wave. It's -10. It's the distance between two corresponding points on adjacent waves.
Why does it make it like so like difficult as a definition?
It's not, because the waves have to be, first of all, side by side. Adjacent waves mean the waves have to be side by side. And you have to pick corresponding points. Meaning, let's just say we pick the top point. Does anybody remember what this top point is called?
It's already used. Parabola.
Science education is so lacking. Has anybody ever heard it called a crest before? Hallelujah. Anybody heard the name of this lower point? What? Trough. Hopefully all you.
I know what that is.
The trough
Oh, I remember that one.
and a crest. Okay? The trough and a crest. So, let's just say for a second that we go from the highest point, which is the crest, to the highest point on this wave. That is the wavelength. But do we have to go from a crest to a crest? Exactly. But we don't even have to do that. Okay? That would also be a wavelength. We could say, I'm going from this point right here, part of the way down on this wave, to this point, same point, part of the way down on this wave. That would also be a wavelength. It just has to be the same point on the very next wave. Yes, ma'am.
So could you do like the top of the crest and the bottom of the trough?
No, because it wouldn't be a corresponding point on the next wave. It has to be the same point on the very next wave.
Okay, so they're like top, the same as top part of the
They're not the same point. That is correct. Okay? Yes. So you can't go from a trough to a crest.
I get this.
It just is.
I'm not saying trough, I'm thinking like a trough. I'm thinking of like
Okay.
an animal.
Oh, right. The unit. We're measuring a length, so the unit can be in centimeters, can be in nanometers, which we're going to use, and the SI unit is meters. The symbol that we will use, oh man, this is time. Is lambda, the upside down line. Yeah. Symbol is lambda, the Greek letter. Lambda. Yeah, like lamb, like that. So if the whole alpaca thing doesn't work out, maybe I can become a sheep herder.
Whatever you found. My mom or Christmas, I'm gonna give you a little stuff in the glass. I'll get you a shirt that says alpaca. You can wear it after the day you retire. The day you retire, everybody gives us something to do with alpaca.
I'm telling you, I'm going to become an alpaca farmer. Seems like it'd be pretty low maintenance compared to teaching teenagers. All right. Frequency is the number of waves that pass a given point in a given amount of time. Okay? Number of waves that pass a given point in a given amount of time. Now, when you draw this, make sure your waves are the same as mine, or when we calculate frequency in a minute, your frequency is going to be wrong. If you go back to look at your notes, you're going to be like, this makes sense. I said, when you draw this, make sure you have the same number of crests and troughs as I do, or it's not going to make any sense when you go back to do this.
I didn't know what you were. I couldn't even talk. I'm my teachers, and I didn't have time to draw with a big mouth. I'm a black kid. I didn't even know that they have ears, so I think it's like a mouse. I could be a mouse. I could be a little mouse.
I think you guys fit better than Black Panther.
I have the heart of a
Okay. All right, everybody caught up?
You're a cat. I'm not a cat.
All right, so tell me this. So we're going to find frequency. So frequency is calculated by doing what?
I need a point.
The number of what?
Wait.
Over the what?
Point.
What's it say?
You've been pointing amount of time.
Over the time. All right, let's just say, we're going to make our math easier because we're long way. We're going to say our times in 1 second because I'm lazy that way. So, how many waves do I have? Well, the first thing you need to know is what makes up a wave. What do you have to make up a wave? A crest and a trough. So, I have how many crests and how many troughs? So, this would be one wave. A little too many things there.
Yeah, well, you do better than my teacher. That was me. You told me.
Well, I'm on YouTube a lot. I record every day.
I know.
So, if we look at the wave, I have how many waves? I have 3. Okay, so I have 3 waves over what time? So my frequency is 3. Now, my unit for frequency is a hertz. Okay. Abbreviated HP. So that's the unit we're going to put on the end of it.
One fly.
What's one fly push-up?
That's why wind that goes.
Really?
Well, I was told
Really? All right. Learn something new today. That's cool. Well, usually when I see them, if I can squat them, they don't get to do any more push-ups. No, they do not. Did you look up SBF?
Yeah.
What was it?
I can't remember, but I got it. Factor, self-protection factor.
Sun protection factor. Okay. Now, it stands for, all right, a Hertz is a cycle per second. All right, so, symbol. Because we're going to have an equation with this. The symbol is an italicized V, but I cannot draw an italicized V, so I'm just going to put that there. And it's again a Greek letter. The Greek letter is nu. All right, but on the test, I can italicize the V because, you know, we can do that on a computer. I cannot italicize the V with my handwriting.
Wait, underline, like in English when you're writing it, you underline it.
Oh, it's H.
Oh, yeah, yeah.
Yeah.
All right.
You got the 3 with H. That's it.
Wait, so the reason
Yeah. Where? Here? That's the V. That's the symbol. That's the symbol for frequency. HZ is just the unit. That's the name of it. So we call this nu.
Oh. So it's not the-
It's the Greek. That's the Greek letter nu.
Oh, good.
Okay. Everybody there? All right. So how are frequency and wavelength related? The last thing we're going to do today, because I'm going to run out of time. They are inversely proportional. What's that mean in math class?
One is negative without it.
All right, opposite. I like that one. All right. If one goes, there you go. All right, if one goes up, the other goes down. The equation is C equals lambda nu. This is not on the reference table. You're going to have to know this one. C is the speed of light. It is a constant. You have to memorize it. 3.00 times 10 to the 8th meters per second. Now, just to illustrate, now, you've seen a meter stick. In 1 second, the speed of light moves 300 million meter sticks in 1 second. The only thing that has moved faster is a group of scientists claim that they've moved a particle in a particle accelerator faster than the speed of light. Nothing else has moved faster than the speed of light. Okay? Yes, we've broken the sound barrier with planes. Chuck Yeager did it back in the 70s. But we have not moved a vehicle, a plane, or anything else faster than the speed of light. Okay? I would be seriously surprised if any of us move faster than the speed of light in your or my lifetime. What is our homework tonight? Study for the test. The actual questions of search and rescue are already on the website. So you don't have to have those written down. It's just on everything that you guys have just reviewed. I will see if I can upload the answers too for those of you who didn't finish.
We go straight to our club. Yeah.
Yes, you go straight to the club with the bell ring. Here.
My club's doing this one.
Oh, good work, Lord.